Chapter 2.1, solution curves without a solution. Question number 24. We have dy by dx is equal to 10 plus 3y minus y squared. So this question is asking us to determine the critical points of the differential equation, in addition to the phase portrait and determining whether the critical points are stable, unstable, or if they're semi-stable. So the first things first we want to do to determine critical points is set the derivative equal to 0 and find those values. So we'll write this thing here. We'll say 0 is equal to negative y squared plus 3y plus 10. Okay, from here we can factor this, and I won't go too much into detail just because factoring should be something that we're all comfortable with. So we know that this becomes this expression over here, and therefore we can say that y1 is equal to 5 and y2 is equal to negative 2. And these are what we call our critical points. So let's call these CP. Okay. Next, what we want to do, I guess what I do is I try to show the behavior of this function on a 2D line, okay? So what I'll drop down over here is my critical points, so negative 2 and 5 here. And I want to look at what's happening on the function on the left, in the middle, and on the right of these regions, all right? If I look at the coefficient of my y squared term, I see that it's negative. So naturally, using the pattern of a polynomial of the second degree, I can say that everything happening before negative 2 makes the function negative. That is, if I were to plug in negative 3 or negative 4, this term over here would return me a negative number. In between, it's going to be positive, and after, it's going to be negative. If you need to check on your calculator, you could do that. Again, plugging in 0 or something here, or plugging in positive 1, and on this side here, plugging in 6, and then seeing the answers that you get. So now that we have the behavior of this quadratic function here, we can now show the phase portrait. So on the phase portrait, what we'll do is we'll draw some sort of vertical line here. We'll call this the positive region, and we'll call this the negative region. All right. We'll then label down our critical points, so negative 2 and 5. All right. Before negative 2, we know that the function is negative, so it's going to tend towards the negative direction. We'll put a downwards aiming arrow. Okay. In between negative 2 and 5, we know that the function is going to be positive, so we'll put a positive arrow after negative 2, tending towards the positive direction. And after 5, we know that it's negative, and therefore we'll put a downwards arrow here. Okay? So when we want to determine the stability or instability of the critical points, we want to look at basically the net influx of the arrows that are pointing at these values here. So at negative 2, we see that both of the arrows are pointing away from it. So what we can call this is a repeller because it's repelling both directions. So we'll say that negative 2 is a repeller. But at the same time, we see that positive 5 is also gaining the top arrow and the bottom arrow here. So we can call this an attractor.